My goal with this video is to get you to think about how much we can really know about the world. You could think of how certain can we be that the laws of nature are really true, that there is preservation of energy, that gravity works in the way we expect it works. But you can also take it a little bit closer to home and look at my research group, for example. We are looking at predictable performance of distributed systems. We are, for example, trying to make sure that when you send a packet over a network, that it arrives on the other side before a certain deadline. And there are projects in which we look at Internet of Things protocols, and we try to make sure that a wireless sensor network that uses such a protocol does not drain its battery, the batteries of its devices that are in it, too quickly. And to achieve this, we use models. We, for example, describe formally how the protocol works to make sure that there are no deadlocks in it, that it doesn't stall for some reason. And we use a worst-case performance analysis to make sure that the traffic shaping that occurs in a network does not delay a packet beyond the given deadline. We can use simulations if we want to know what the average energy usage is in this wireless sensor network that makes sure that the batteries do not drain, or how much the batteries will drain, or how long the battery life will be. But as any physicist will point out to you, these models are only as good as, well, they adhere to reality. So the only way to really be certain about our modeling is by comparing it to reality. In other words, by performing experiments. That interchange between modeling and experimenting is what I want to talk about in this lecture. All science starts by looking at the world, just observing what happens. And if nothing happens and you get a bit bored, you may consider to poke the world a little bit and make something happen, but it's all about getting something to happen and observing that. And when finally something interesting happens, you write it down. You've made your first observation, so to speak. Something like, you write down, when I push an object, it moves. Or when I ping the Google server, a response comes back within 8 milliseconds. Next, you start thinking, what just happened? Can I explain it? And you make your first guess at a possible explanation. Could be completely wrong, could be a hilarious guess, but you make a first guess, and that first guess we call your first model. The process of writing down what your guesses are is called modeling. So now we have a model. At this point, scientists split into two groups. There's the engineers and there's the physicists. And an engineer's first thought, once the prediction seems to fit what he observed, is, can I make it happen again? Maybe in a more useful way. What an engineer does is he starts to use his predictions, which he also calls calculations or simulations, to calculate conditions under which the phenomena that he just observed happen again. And sometimes, in order to make it happen in a more useful way, he will need a few more experiments that he uses to feed back into his model. And that's what we call estimating. The engineers try to recreate the conditions they calculated in the real world. And if they were right, then, whatever they predicted happens again. The arrows in this diagram, we say they start to commute. In other words, engineering plus experimenting will give the same outcome as predicted using the calculation. And everybody is happy. But wait a minute, say the physicists, the second group of scientists, just because your experiment worked out, that does not mean that you understood anything. Only if an experiment fails you know that your model is wrong. If an experiment works out, that might just be coincidence. Yeah, coincidence, say the engineers. We actually worked hard enough for it. We did all these calculations and we made it work, right? But the ones who really worked hard enough for it were the physicists in the first place. Because a physicist actually does the same thing as an engineer. Physicists also make calculations on models and they predict under which conditions what will happen. They call these conditions hypotheses, and then they try to create conditions in the world to see if their hypothesis holds. But the difference is that a physicist is actually not trying to make something useful happen. A physicist is actually actively trying to find experiments that go wrong. It's annoying, they just want to prove the model wrong, but in their defense they do this because the only way in which we can learn something is by proving that our thoughts were mismatching. And when engineers rely on physical models, they are actually relying on the fact that physicists have been trying to prove these models wrong for a very long time and so far failed. So probably the engineers can, do some more experiments within the bounds within the physicists already tested the model, and then everything will work out fine. So you may say that the difference between an engineer and a physicist is that an engineer is happy when things go right, and a physicist is happy when things go wrong. Now, how is this useful for the upcoming module on basic statistics? Of course, a probabilistic model, a distribution, is just a way to express what you expect as an outcome of an experiment. And statistics is just a way to estimate the parameters of a probabilistic model. So engineers, even though probabilistic models do not really provide an explanation of any of the mechanisms behind whatever happened, engineers can use these predictions to at least make sure that something useful will happen within a certain number of tries. And the scientific method also holds for this kind of models, because using experiments you can only show that a certain hypothesized distribution is wrong. You do a lot of experiments, you get a certain graph, but the fact that you get that graph is not really an affirmative that this is the distribution. Only if you get an outcome that does not match with your hypothesis, you can conclude, oh, this is not really the distribution after all. And that's what we will see and what we will learn in this module. We will actually learn to compute what the probability is that a certain set of experiments contradicts the assumption that the experiments were behaving according to a certain distribution. And we can actually calculate that probability quite precisely. In contrast, we can never confirm that a certain distribution is the right distribution at all. Apart from this, there is another lesson that I would like you to take with you from this video. Of course, the distinction that I made between engineers and physicists is completely made up. Every engineering work needs a little bit of physics, every physics work needs a little bit of engineering. A scientist is usually a mix of both. But I made that distinction so that you can make clear to your audience when you're reporting why you are doing the things that you're doing. For example, the choice of parameters in an experiment is different when you're going for an engineering purpose or for a physics purpose. If you're looking to make a design that works, then you will actually be doing experiments and simulations and calculations around scenarios that are realistic for the operating conditions that you want your design to be working in. when you're actually trying to check whether your modeling is right, when you're doing the physics, you're checking for understanding, then you will be looking for scenarios and parameter settings that are on the border of where your models are valid. So you're actually doing a different kind of experiments. They may look like the same thing, you're doing calculations to predict certain outcomes, but inherently they are different. And by actually making that distinction in your reporting, you can make it clear to the reader why you are doing certain things. You also make it more clear to yourself because you understand the difference between those experiments. And as I said, any scientist has to do a bit of both. So in the reporting that I look at for my students, I usually check whether I see both elements and whether I see an understanding of both elements in the reports that I get to read. I hope that this video gave you a clear impression of what I mean by the scientific method. At the end of this module, there will be an assignment, and with that assignment comes a rubric for grading it. You will be peer reviewing each other's work. When you interpret that rubric, I of course hope that you will recall the contents of this video.